And you can see my screen, right? Okay. Yeah, hope you can see my screen. So what we'll be doing today is we'll be talking about backpropagation. And specifically, we'll be looking at backpropagation in neural networks. So I'll first talk about an example explaining why it is important and what is its role in deep learning. And finally, in the end, we'll hopefully solve one or two questions regarding backpropagation. So to begin with, the basic idea of deep learning is that you have some input data X. So you have some neural network which gives you an output Y, and our goal is to be able to predict Y using this neural network using training data given by Xi, Yi, which means that for every data point Xi, Yi is its corresponding output that you want to have, or that you want to have predicted by the neural network. So basically, what the goal of neural networks is to minimize some error using the training data, and hopefully learn the neural network so that it can perform well on some test data or test examples. So so just to give a basic idea of how learning works and how backpropagation is done is that let's assume that I'm learning to play a sport, let's say tennis, and I have maybe I have a tennis court like this, and my goal is to hit the ball into the court as much as I can, and I want to prevent hitting the ball outside the court, something like this. Now, what this means is that every shot that my opponent plays against me, I want to return it such that the ball lands inside the court. And we want to avoid hitting the ball outside the court. So what this means is that we are training our muscles and our nervous system to be able to hit the ball inside the court. And how do we learn this? Is by minimizing this distance, or the so-called error. Okay. So this error is what we want to minimize, or maybe the error is from somewhere inside the court. So this is what we want to minimize, and as we keep practicing, our muscles develop that skill to be able to hit inside the court, while at the same time minimizing this error. So that is the goal of learning neural networks, that is to accomplish some task by reducing some form of error. So this is the goal of neural networks or deep learning in general. So what are the different phases that a neural network has is that first, okay, maybe I'll just copy this. So a neural network is typically accompanied by two operations. One is the forward pass that takes input to output. So forward is input to output. And we have something known as the backward pass and the backward pass goes from output, or in most cases the error, to the weights or input. Okay, so the forward pass is what the neural network predicts, and the backward pass is the feedback that you get from the prediction that is made by the neural network. So based on this feedback, whatever is given by the backward pass, we can choose to update our weights accordingly in order to reduce an error. Okay, so that is the basic idea of every neural network in simple terms, and we are going to focus on this backward pass and or back propagation in general. Uh, uh, so what I'll do now is we'll set up a simple neural network and we will see how back propagation works. So the neural network is as follows. Uh, you have some input, let's say x, and it's a two length feature vector. So x1, and a neural network typically has these neurons or nodes. They're called neurons or nodes. And this is where multiple operations happen in the neural network. And it keeps, and every neural network has things known as layers, and each layer consists of multiple neurons which are interconnected with each other. So this is typically how neural networks are. So this is known as the input layer. This is the input layer, and then we have two hidden layers, and finally we have one. Let's say we have one output layer, giving us y hat, which is the prediction. This is the prediction or the output, and this is the input. So, like I said, these neurons or nodes are where the operations happen, and each of these connections. So maybe I'll highlight it. These connections are these connections link two nodes through some weight characterized by W. So every node I'm going to notate with the letter A. So maybe I'll call this A. This is A1. This is the first node in the first layer. This is the second node in the first layer. So I call them A11 and A21. And these weights are denoted by Wij. It connects, Wij connects node I to node J. And of course, every weight also is also associated with the layer number. So this, let's say this is layer 1. So Wij1 is node I to node J from layer 1. So this is the notation that we're going to follow. And similarly, the output layer, I can denote the hidden layer I can denote by the notation A12, which is the first node of the second layer, and A22, which is the second node of the second layer. And finally, we have y hat, which is the output. You could call it A13, but it's just simpler to call it y hat, which is the output. So this is the notation we're going to follow. And yeah, so this is the notation we will follow. And the weights are denoted by Wij, Wij of the layer number. So this weight, for example, this weight over here would be denoted by W21 second layer. So W21 of 2. So now that we have defined the notations, so let's move forward. So like I said earlier, the goal is to minimize some error using the training data, and this error is also sometimes also called the optimization objective, or it's also called the loss function. So a loss function is some function of your prediction y hat and your input x. It is some function of this along with the parameters. Okay, so maybe I'll also mention that. So let's say all the wij's are in some vector. They're the collection of all these weight vectors, wij of any layer L. So let me call L. So this theta is the set of all parameters in the neural network. So yeah, and it's a function of theta. Okay, so this is typically what is done in neural networks, where you try to minimize this. So our goal is to minimize over all possible theta this function of I hat, x, and theta. So you want to reduce the loss function using training data. Okay, so let's maybe copy this. Okay, so the one of the most common loss functions that we use is known as the mean squared error. In short, we just call it MSE. It is nothing but half y hat minus. So let's call the neural network f f theta, parameterized by theta. So f theta is the neural network. Y minus f theta of x squared. So this is known as the mean squared error, and this is what we want to minimize. Okay, so in order to minimize any function, the most there is a hand raised. So
yeah, I have a question. Can you please just tell me what the theta denotes? Sorry, I mean, I did not understand it fully.
okay, yeah, sure. So theta is the set of all weights. These connections I told you, right? These neural connections. This connection from A12 to A21 to A12. So things like these are connections between nodes of the neural network, and these are parameterized by some weight.
Okay.
So those weights are what, if you collect all those weights and put them into one set, those are, yeah, sorry. Yeah, so I was saying the theta is the collection of all weights of the neural network. So I'll write theta as W11 of 1, W121, W211, W22 of 1. So if you look here, this is going to be W22 of 1. This weight vector connecting this is going to be W21 of 1. This is going to be W11 of 1. And this weight vector is going to be W 1, 2 of 1 because it connects node I to node J. This is node 1, this is node 2. So the weight connecting node 1 of layer 1 to node 1 of layer 2 is going to be W11 of 1, which is this. So by what I mean by theta is it is the collection of all these weights in the neural network. Okay. So it's just a set of connections that we want to learn in the neural network. So I'll come to how we learn these. So does that answer your question?
Yes, thank you, sir.
Okay, sure. Okay, so moving forward, like I said, our goal is to minimize this loss function, and that helps us reduce our error and learn a particular task properly. By learning a task, I mean these predictions y that we get, we want them to be uh, we want them to be very good or close to what we desire. So that is the goal of learning a neural network. Um, so let's so let me begin with a simple example maybe. So let's say this is your input x. Yeah, sorry. So let's say you have two inputs to your neural network, x1 and x2. Say this is your node. So these are your input nodes, a11, and this is a2 of 1, meaning layer 1. And then you have the similar neural network like this. You have a single output node giving you y hat. And let's say that, okay, let me just notate these. This is A1 layer 2. This is A2 layer 2. And this weight over here is W111. This going from node 1 to node 2 is W12 of 1. Similarly, you have W21 of 1 and you have W22 of 1. Similarly, the output layer you have W11 of 2 and W21 of 2. Okay, so so what we're going to do is we're going to assign some weights to these, and then we will see how this neural network is trained. Okay, so let's say this W11 is just, okay, I'll erase these and maybe just put the weights on top of the arrows. So this maybe is 1, this is 0.5, this is 0.5, and this is 1. Similarly, let these output weights also be 1 and 1. Okay, so for the input nodes, we have A11 is simply equal to x1 and A21 simply equals x2. Okay, so this is what we have. This is the input layer. Then the notion of nodes in a neural network is as follows. It combines different nodes of the previous layer through something known as a linear combination or a weighted sum of the previous of values in the previous layer. What I mean by that is, let's take A12 for example, which is this node over here. A12 equals a weighted sum of A11 and A21, and the weights are exactly what is there on the arrows connecting the corresponding nodes, which is W111 and W21 of 1. Okay, so this is typically how A21 is defined as. But one important thing to notice, before, it is not just a linear combination of this, it is some function g of this function. Okay, so this g function is known as an activation function. And depending on the application or what you want your neural network to achieve, these activation functions could be different. For example, you have sigmoid, you have ReLU, you have tan h, and each of these activation functions do something different. So sigmoid is sigmoid of x is 1 by 1 plus e power minus x, and the ReLU function is nothing but g of x equals x when x greater than equals 0, 0 if x is less than 0. And yeah, similarly, you have other activation functions like tan h, exponential linear unit, and you have many more. You have so many activation functions that are used on the linear combination that you get from the previous layer. Okay, so this is the activation function. This is sometimes also known as the net input to the node. Okay, and what we have here is the node output. Is the node output or simply the okay? So let's not call it output. Let's just keep it as node output. So this is yeah one question, yeah two questions.
Hi, sorry. Am I
Yeah,
audible?
yeah. Tell me.
So I just wanted to know about why we in the middle layer, right? Can we scroll a little up? I wanted to see that figure. Yeah. Why is there no connection between A12 and A21? Can that also be called as a neural network? I mean,
No, typically that's not how. Okay, so let me give you the let me give you a real life example. So every living being has a nervous system, right? So in that nervous system, you have some neurons that are like this,
okay.
and then you have these synaptic connections connecting one nerve to another. Okay,
Okay.
so okay, I think my screen is yeah okay. So what these nodes are is actually this point, the starting of the branch that connects one node to another node. So these nodes are typical like let's take the optic nerve for example. So the optic nerve is typically a bunch of nerves. So these bunch of nerves have separate nodes in each of them, and they are typically when you have multiple connect when you have a bunch of nerves like this, you don't really need these two nodes to be connected, say,
Okay.
because the main reason is if let's say some problem happens with this nerve, then if these two are connected, then this whole line is gone. Like this whole since this entire nerve is connected, then this could cause problems. So uh, like essentially what we are trying to do is we are trying to parallelize these nodes so that
Okay.
if one thing goes wrong, you can always learn with another node or things like that. But of course this is not an exact answer to your question, but typically this is the convention that you follow in deep learning and neural networks.
Got it.
You don't
Yeah.
have okay, so you don't have connection between these because you have a very nice dense connection between these nodes, between
Got it.
layers of nodes. Okay,
Got
so
it. Yeah. And
that's
the sorry,
there's
yeah.
another
Just to follow up,
yeah.
and the difference between A12 and A22 is actually the weights currently, right? Because both are giving the same inputs, but with a different weight. Both are
Correct,
getting
yes.
X1 and X2, but weights can differ, right? That's it, right? Yeah.
Yeah, correct. So
Okay.
you can notice that if x1 and x2 are different, then a12 and a22 are different, right? Because if you look at a12, it is some function of w11 a1 and w21 a2. But if you look at a22, it is the activation of, so A22 is this one, right? So A22 is this one, and it comes from, so what are the things contributing, what are the nodes contributing towards this? These two, right?
Yeah.
So,
Mm.
so in this case, it's going to be W121 A11
Yeah.
plus W221 A21. Okay.
Okay.
So you
Yeah.
can see that these two are different, right?
Sure. Yeah. Got it. Yeah.
Yeah.
Thank
So
you.
yeah. Okay. So basically, this is how we go forward in a neural network, which is taking the input to the output, and this entire process is known as the forward process. So the forward process takes you from input to the hidden layers. Of course, you could have multiple hidden layers here. You can have A12, A13, A14, and then you can have I hat and things like that. So those are deeper neural networks, and that's where the term deep learning stems from. When you have more than 3 or 4 layers, you typically go into the realm of deep learning. And yeah, so this is a forward process, and so let me just complete the equations for sake of completeness. So similarly, this is W11 of from layer 2. This is weight connecting node 2 to node 1 of layer 3 from layer 2. Okay, so y hat is again some function of W112, but it multiplies this node over here, which is A12 plus W212 of A2. Okay, so this is the final output, or you call it the prediction of the neural network. Okay, so this is the entire forward process, taking you from the inputs to the output. Okay, so typically your input is denoted by x, and it's a vector containing x1 and x2. So you could call this input data, or you could call it features, input features. So yeah, these names are used interchangeably. So you just basically, this is the input. So the input could be a vector, it could be a single number, it could be an image, it could be anything. It could be a video, it could be an X-ray scan, it could be anything. So depending on the dimension of the input, your neural network will also change the nature of its weights. And one important thing is that for every, so I'll just copy this once again.
One question I have.
Yeah, sure. Go ahead.
So does this follow an additive property where G of W112 A12
Hmm.
can we move double weights can we apply the function on the different weights then add them, like G of W11 A1 plus G of W21 A2?
Sure, you can definitely. It is possible, but generally in neural networks, for a particular layer, you have a particular G. So, for example, layer one. So, okay, maybe this layer could have a ReLU activation function, and maybe this can have a sigmoid. So G is equal to ReLU. Here, G is equal to sigmoid, and you generally have different activation functions for different layers rather than different activation functions for different nodes. Okay.
Get it.
Okay.
Thank you.
Yeah. There's another question.
Just a small query that how initially we are
Hmm.
assigning these weights. I mean, I understand later maybe through the back propagation we correct it, but initially we have to assign some numbers against
Yeah.
these weights, right?
Yeah. So I was so that was going to be my follow-up discussion.
Okay.
So
Sorry.
yeah, no, it's okay. It's a good question actually. So one important note is that weights are initialized. So what I mean by initialized is they are assigned something. So you are assigning some weights at the start. So so typically what people do in neural networks is that these weights are selected randomly, or I should say initialized randomly. Okay. So yeah, I have a couple more questions. Yeah.
Sir, what is the significance of this activation function? Like, will it be covered later? Or...
Yeah, I mean, okay. So the role of the activation function is to limit these outputs, these node outputs, to be in a certain range. So you don't. Okay. Yeah. Sorry, I got cut off. Yeah. So I was saying the role of these activation functions is to somewhat limit the values of these node outputs. So you have these node outputs, right? A12, A22, and all these things. So you want to limit them to a certain range. For example, if you take the sigmoid activation, so g of x is let's say sigmoid of x, which is 1 by 1 plus e power minus x. What this basically does is that uh, okay, we'll use this color. What this basically does is, if you have, let's say this is your x and y axis. Uh, okay, y is equal to sigma of x. What this does is that it takes all your values from minus infinity to infinity, and it brings it to the range of 0 to 1. Okay. So in neural networks, you don't want your values to blow up so that your y hat becomes like 1 lakh, 10 lakhs, and all. So you don't want that to happen. So you want to control your Hmm?
Yeah, we want to like contain it in some range.
Correct. Yes. So so activations basically control your node output. So these activations are actually very important because this sigmoid, right? This is the sigmoid function. This is used typically at the output of classifiers. So classifier is basically something that gives you a decision. So it gives you a decision, and you basically want a yes or no decision. And so, for example, yes could be close to 1 and no could be close to 0. So the sigmoid activation function is a perfect choice as an activation function in these classifier functions. Okay, so sir will be covering classifiers later on, and maybe that time you'll encounter the sigmoid activation. So depending on what you want your network to do, you will choose different activations for different layers of your neural network. So for image problems, you might want to use ReLU. So for for image networks, you might want to use ReLU, which ReLU is basically anything less than 0, it gives 0, and anything greater than 0, it gives the same output. So this is the ReLU function. So x and g of x. Yeah. So this is so depending on your application, you will decide to choose different activation functions. So hope that's clear. Yeah, there's another question.
Weights and biases that they are very small in number. They're not big. I believe the
Sorry.
reason you just gave, you don't want to blow it up. Is that correct? Or and when we
sorry,
also
yeah,
please.
your voice was breaking in the middle. Can you repeat the first part of your question?
Yeah, generally what I've seen, the weight and biases for this neural network, they are very small in numbers. They are not pretty big.
Correct.
So there has to be a reason behind that. I believe you just explained we don't want to explode the final y hat.
Correct, yes.
Is that okay? And second thing is that when we initialize it randomly, do we also define what kind of?
I think I'm losing your voice. I can't hear.
Okay, let me try once again.
Yeah.
So when we initialize these weights randomly, do we also define the range between it's going to be?
Correct. Yes, we do. In many applications, you use some weights between 0 and 1. Okay. Ij belongs to some, let's say, -1 to 1 or 0 to 1. So typically, we choose weights in this range, and we initialize weights randomly such that they're in this range, -1 to 1 or 0 to 1, just so that it's small and you don't have something known as gradient explosion. You want to avoid this gradient explosion. So I'll come to what this is later on, or it will also be covered in the course, I believe. So we want to prevent this. Want to prevent gradient explosion, so we choose the weights to be a bit in some range where they are very small. Yeah. So I hope that answers your question for now. So this you will encounter in almost any application where the weights are going to be very small, and you start off with those weights, and then you start learning your network through backpropagation. Okay. So now let's move to backpropagation. So let's go back to our neural network that was over here. Yeah. So this was a network, and if you recall, we had a loss function L, which was the mean squared error between y hat and f theta of x, where f theta of x is taking your is the entire neural network. This is f theta of x. This takes your input x, where if you recall, x was the vector x1 x2. This is the vector. This is a input vector of x1 x2, taking you to the prediction y hat. This is the prediction. So what we basically want to do is, let's say we have some training data, and for now let us assume we only have one training data sample, which is for the input x, I expect the output y. So this is our training data. So typically you call it xi, yi, and you have n such examples. So your training data will typically look like x1. For x1, you desire the output y1. For x2, you desire the output y2, and so on. Okay, so this is our training data. But for now, let's just assume we have a single training data sample. Assume your data is just x comma y, a single example. Single training example. Now, our goal is to minimize L is equal to half of y hat minus f theta of x squared. So this is what we want to minimize. And how do we minimize any function? we compute its derivative with respect to what we can optimize over or what we can change in the network. And what can we change in the network? We can change theta or the weights. So this is what we can change. So the natural step is to take the derivative of the loss with respect to some parameters in the network. So let's say Wij of L, which is the weight Ij, weight from node I of layer L to node J of layer L plus 1. And we take this derivative and what we do is we compute this derivative and then we do something known as the gradient descent, which is any weight Wij of L is updated as Wijl minus some weight alpha times this derivative Ijl, and this is known as back propagation. This is back propagation through gradient descent. Yeah, there's a question.
Sir, in this minimize loss function, this y hat is also the output of this neural network. Y hat is also the output of neural network, right?
Yeah. Oh, sorry. Oh, yeah. Sorry, I missed y hat. I wanted it to be y.
Y.
So okay. Yeah. Sorry, my mistake. This should be y. Yeah, correct. Thank you.
Sir, I have one question.
Yeah.
So I have a general doubt. So when we calculate the loss in a network, the network is not aware of the loss function, right? Initially, we just calculate a numerical loss and it's some numerical data which we have.
Correct.
And then how do we calculate the gradient on some numerical data with respect to a parameter? Just wondering.
So, okay, yeah, that's a good question. The loss is what we define. This is user defined. So this is a function, and it is a function of x and theta, correct? So regardless of whether your data is numerical or synthesized or analytical, whatever it may be, you can always compute the derivative of your loss with respect to your parameters. So since this is what we define and it is a that we define, we can compute the gradient of this and we can use that to update our neural network. Okay. Is that clear or?
Yes, sir.
Yeah. Another question.
Sir, I had a doubt on the loss function. So since this is a squared value, like how do we know if we're shooting above the value or we're shooting below the value in that scenario?
So you have your prediction, right? Y hat from the network.
Yes.
So this is the prediction. And what is y hat? Y hat is actually f theta of x. It is what your neural network gives you. So what your neural network gives you is the prediction, and what you have is your training data xi, yi, and what you will do is you will compare prediction y hat equal to f theta of xi. Xi is some training example that you have with the ground truth yi. Okay, so maybe let me call it y hat I. So what you will compare is you will compare the loss between y hat I and yi, which is the squared error y hat I minus f theta of xi. So you have your prediction over here. sorry, oh, I shouldn't use. This is yi, sorry. And this is your true label or ground truth. So ground truth is what we desire, and prediction is what your neural network has given you. So you have an idea of which one is greater or lesser. Okay, is that clear?
Yes, but the loss will be the same. Like even if the f naught, the prediction is higher, for example, by 5 compared to the truth, or if it's lower by 5, the loss function will give you the same value, right?
Yes, it will. Yeah.
So then how do we know, like, we have to increase the weights or we have to decrease the weights in that scenario?
So that is what, so the moment you have some error that is not zero, that is greater than zero, it means that you are off from your ground truth, correct?
Yeah.
So you gave the example that f theta of xi might be 5 higher or 5 lower. It means that your loss is half into 5 square, 25 square by 25 by 2, that's 12.5. That means that there is some difference between your yi and f theta of xi that you want to minimize. You want your f theta of xi to be as close to yi as possible. So that is when you have a loss that is non-zero, that is what you want to minimize as much as possible. And that is what will update your weights, and it will tell those weights. See here, with your current value, you're giving an error of 12.5, but can you update it so that 12.5 becomes lower? Okay, is that clear?
Yes, thank you.
Okay, great. Let's go ahead. So so this was our back propagation equation. Maybe. So this is.
Sir, this alpha is some constant.
Yeah, I'll come to, yeah. So this alpha over here, this is a constant known as the learning rate. Okay, so what basically we want to do is we want to update our weights in a way that a change in the weight reflects as a change in the loss function. Okay, so if I change Wijl is our general expression for any weight. If I increase my weight some amount, I want to see how much does the loss decrease. Okay, so this is typically uh, the this is typically what neural networks do. When you change a weight by delta W, how much does the loss change? And that loss is delta L. And we want to see the rate of change of the loss with respect to the weights, which is nothing but the derivative of the loss with respect to the weight. Okay, so this is the rate of change of loss with respect to weight Wij in the layer L. Okay, so I hope learning rate is clear. So every weight in the neural network is updated according to this. This is the gradient descent, meaning that every weight is updated by some constant times the rate of change of the loss with respect to that weight. Okay, so I hope this much is clear. If you have any questions, you can ask until now. I'll go on to derive the
one query.
Yeah, go ahead.
Yeah, this constant will be common for all layers.
Yes, it will be constant for all layers, all weights.
And how do we find that? That's what we are going to discuss. Sorry.
No. This is not found. This is something that we set. Okay, and parameters that a user sets are known as hyperparameters.
Okay.
meters, and these are fixed by a user.
Got it.
Okay. Okay.
Thank you.
Okay, great.
And,
So,
sir, one more question.
Yeah, tell me.
In one back propagation, like every weight is reduced. This derivative is with respect to each separate weight, or like it's with the entire.
Good question. This weight update is done usually for all the weights of the network. So every WIJL will have its own update, because one is you have the weight itself, and then this term is specific to the weight WIJ. So every weight is going to be updated in a neural network typically. Okay.
Okay.
So for every weight, you will have this update equation. You will have a different update equation, and the gradient in the update equation is going to be with respect to a particular weight that you're choosing.
Okay.
Okay. Okay.
Yeah, one follow-up question on that. So
Sure.
just assume that for some of the layers, the gradients is really small, and I have to freeze those layers. I don't want to calculate derivative for some of the weights, but only to the initial layers of the network. So will that also be allowed?
Sorry, I think I lost your voice.
Yeah, I would repeat. So just assume that in case our gradients are very small for the deeper layers of the network, and I don't want to calculate the derivatives for the deeper layers. I only want to calculate the derivatives for the initial layers. So is there a freezing of the weights or freezing of the layers allowed during the back propagation, that if I can just freeze the weights for some of the layers and only do a back propagation on few of the layers?
Of course, you can do that. Of course, you can. Uh, and typically, this is done in many applications where you freeze a portion of your network and only update certain weights. It could be the later part of the weights, later part of the network. It could be the earlier part of the network. You could definitely do anything you want. And what weights you choose to update is completely up to you, and it depends on the application that you're trying to learn a neural network for. Okay. So you can definitely do it that way, and that's a very good question actually. And many applications, in fact, do this. So it is known as transfer learning. So transfer learning, where you freeze a part of a network and train few weights. So yeah, that is a good point. Yeah. So you can freeze a part of the network. Okay. So let's take an example and see how backpropagation is done. And this backpropagation that I'm going to talk about is general for any neural network. So any neural network uh, will involve backpropagation, and it is the foundation, or it is the foundation of all machine learning. Every machine learning algorithm definitely has backpropagation, and it is the most important part of learning any task. So let's take this example again. So what I want to do is I want to update. What I want to do is I want to find a way to update W11 of 1. Okay. So let's take this example, and we are going to see how to update this weight. Now, what we need to do is we need to find the derivative of the loss with respect to this weight. Sorry, dou W11 of 1. So this is what we want to find. And the way we find it is we see what is the path. So what we do is we find the path from W11 of 1 to the output y hat. Okay. So first we identify the path taking us from the, okay, maybe I'll show it in a different color. So this is W11. So here is W11. It goes like this to the output. Okay. So this is the path taking you from a weight to the output. And what we need to find is we need to find this derivative of L, which is the loss function with respect to W11. Now, the way we do this is using the chain rule of derivatives, which says that the derivative of L with respect to some weight is equal to derivative of loss with respect to what it came from. So L by it came from this path, right? So that path is it came from W21, the weight W21. So I want to find. Okay, sorry. Before that, it came from A13. So do A13, and what did A13 come from? It came from the weight 11 of 2, and what did that weight come from? That weight came from. So this is W11 of 2. That came from node A12. And what did A12 come from? That came from W1. So this is the chain rule of derivatives. And you can see that you have a chain of derivatives that you need to compute. And since you're going backwards in the network, this is back propagation. This is, and more specifically, it is the back propagation of error. Okay, so you're propagating the error backwards in the network to the weight that you're interested in calculating the derivative for, and that helps you calculate the gradient update for the weight. Now, let's just give some example activations. For example, let this be a sigmoid. Let this also be a sigmoid, and let's check what these derivatives are. So the first one is going to be derivative with respect to A13 of half of y hat minus the prediction f theta of x, which is A13 3 squared. And what is A13? We wrote it earlier in our forward equations, in the forward process here, yeah, which was this. This is A13. So we had this expression. So since it was a sigmoid activation, we are going to. So this was A13. And what we want to calculate is this second term over here. So derivative of A13 with respect to 11 of 2 is nothing but with respect to 112 of sigmoid of this term over here. W112 A12 plus W212 A22. And
here also it should be y cap, right? Sorry. Here also DL of DA.
Sorry. Keep making this up. Yeah, sorry. Thanks for pointing that out. So it is y minus A13, and so we have derivative of A13 with respect to W11 of 2, which is the derivative of the sigmoid with respect sigmoid of the net input at node A13. And you could try this as an exercise. Show that derivative of the sigmoid function is the sigmoid times 1 minus sigmoid of x. Okay, so you could try this simply as an exercise. So which gives us A13 by dou W11 of 2 is equal to sigmoid of this term into 1 minus sigmoid of that term. So we have the second term. We got the first term initially. We got the second term. Now the third term is W11. No, actually, okay. So we may not need this term. We can just directly have. Okay. So yeah. So similarly, we can find the derivative of this weight W112 with respect to A12, this, and then finally we can get this expression. And if you multiply all of them, you get derivative of L with respect to the weight 1 of layer 1. And what we do is we just update W11 of layer 1 by the current weight current weight minus alpha, which is the learning rate, times derivative of L with respect to dot W11 of 1, and this is the gradient descent update. So this is typically done multiple times. So this is one iteration of learning, and typically you do multiple iterations. So this is typically done multiple times until the weight converges or until convergence. So what I mean by convergence is that the weight does not change too much as you keep updating. So what convergence means is that W11 of 1 doesn't change significantly. Or in other words, alpha times dou L by dou W11 is very small. So as you keep training the neural network, this gradient is going to become smaller and smaller and smaller until it reaches a number very, very close to 0. And that is when you're going to stop training and say that your neural network has learned with respect to a certain weight. Okay. So yeah, so that I think we are out of time. It's 9:36. So this I hope this was helpful in explaining backpropagation and how it helps how it helps learn neural networks. So yeah, any questions before we break for the day?
Sir, one question, like even for the one data, one X, Y, this updation will happen multiple times, right?
Correct, yes. So yeah, okay, that's a good point. Maybe I should mention that also. The training is done, training or weight updates can be done on batches of examples, batches of training data. So what will happen here is that when you have a batch of examples, every weight is updated using multiple inputs and outputs. Okay. So what will happen is that your loss function that you had over here, right? Okay, maybe, yeah, here. So this loss function that that is there here. Okay, I don't want to highlight it. So it will be a sum over sum I equal to 1 to n, and n is known as the batch size. Okay. So yeah, that's a good point. Every weight can be updated using a batch of examples rather than a single example, and in fact, that actually improves your training because you are seeing how a single weight is affected by multiple training examples, so that it works on all of them at the same time. Okay, meaning your yi is close to f theta of xi for all the xi's and yi's in that batch of n examples. Okay. Okay. There's another question. Yeah.
So this means that if we are able to pass the batch of data, you said that the weight updation happened properly. It means if we are passing the whole data set at once during a forward pass, it will adjust the weight even more better way instead of dividing the data into batches.
Correct. You're absolutely right. So actually, having a larger batch size means it reduces the variance of the error. So that is there is some math involved in that, and I'm hoping Pratosh will cover that in class. So basically, what you're saying is right. If you have some data set of n examples and you pass all of them in the forward pass and then update your weight, it will typically lead to better learning and faster convergence of your neural network. Yeah, so you're right. Yes, if you use more examples, the weights will be updated better. Okay. Yeah. Any more questions?
Sir, there is a quiz being mentioned on Saturday. Do you know anything about it? What we should prepare or something relevant to that?
Typically, it will be whatever syllabus that has been covered till the class before the quiz. But I'm not sure if he has mentioned any specific portions. If you want, I can ask Pratosh and let you know again. I'll let you know on the group. Okay.
Sure. Thank you. Yeah.
Okay.
And
so the quiz is at 9 a.m. on Saturday. Yeah.
Sure.
And can you upload your notes onto the Teams what you're writing today?
Sure. Yeah. I'll upload it. Yeah. I'll post it on the group as a PDF.
Thank you.
Okay. 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 I think we can stop for today. So yeah, all the best for the quiz on Saturday.
Thank you, sir. Thank you.
Thank you.
Thank you.